All right, let's define the integral of a scalar field along a path, along a parametrized path in Rn. The big idea, again, is that what we're going to do is add up the values of the integrand along that path. Now, how do we do so? The way that we're going to do it is we're going to take advantage of the parametrization of the path to pull back those scalar values and add them up using a standard integral. Here are the details of how that works. Let's say that you are given a parametrized path gamma from an interval AB into Rn. Then, if you're given a scalar field f, that will act as our integrand. The integral of f over gamma with respect to arc length on that path is equal to a parametrized form where what we're going to do is substitute in gamma of t into f, and then for dl, that arc length element, we're going to substitute in the length of the derivative of gamma times dt, the usual arc length element that we learned about way back in volume 1. So on the left, we have the notation for this integral. On the right, we have the formula for the computation that is using a change of variables to the parameter interval. And the net effect of this is to add up all the values of the scalar field along this path. Given that scalar field, what does this look like? You draw your path gamma and you think of the values of the scalar field restricted to the path being pulled back to the parameter interval when scaled by the arc length elements of the path. Adding all of these up by a standard integral gives you this scalar path integral. Let's see an example of how this works. Let's say we work in 2D to keep it simple, visual. Let's say our scalar field is x plus 2y, and we need to integrate this along a path going from the point 1, 0 to 0, 1 along a circular arc in the counterclockwise direction. The first thing we need to do is to parameterize that path. Let's do so in the obvious way, saying that x is cosine of t and y is sine of t, as t goes from 0 to pi over 2. Now, to compute the arc length element, we're going to need the derivative of this gamma. Gamma prime of t is clearly minus sine of t and cosine of t, from which we see that the length of gamma prime is a constant equal to 1. This is a unit speed path. Okay, now to integrate the scalar field x plus 2y over this path gamma, what do? We integrate using t as t goes from 0 to pi over 2. dl, the arc length element, becomes simply dt because gamma prime is always of length 1. Then what we need to do is substitute in for x plus 2y the terms of gamma. X becomes cosine of t. 2y becomes 2 sine of t. We're integrating this with respect to dt as t goes from 0 to pi over 2. Now that integral's easy. The integral of cosine is sine. The integral of 2 sine is minus 2 cosine. When we substitute in t going from 0 to pi over 2, we get 1 minus 0 minus twice 0 minus 1 for a net answer of 3. That means when you're adding up the values of this scalar field, x plus 2y, along the circular arc gamma, what you obtain is a final answer of 3.